back side. Notebook back side. Somewhere. Let me just check whether I left it outside. Somewhat compact notes. Just before going for coffee. Did anybody pick up a notebook that was here? Here, if PK pick it up, then he can say. No, I wonder if PK has taken it actually. I think he has. Okay, since this is the last lecture, and there were a few different things that I wanted to mention at least, if not talk about in some detail, so I actually prepared some notes for this one. It is going to be a little bit of, I think, what's called a dog's breakfast, for want of a better terminology, because a few different things that I'm going to talk about. But it will all be focused, let's say, on the theme of mixed state entanglement. So we have discussed bipartite pure states in some detail, seen a few uses, etc. But we didn't really touch upon mixed states. And another sort of related thing which we did not talk about was also multi-party entanglement. And we'll see that the two are also related in some way. But let me start by asking how we would define what is an entangled state in the bipartite setting when the state is not a pure state but a density matrix or a mixed state, right? So I have a bipartite density operator. We say that a bipartite density operator is separable, means unentangled, if it can be written as a convex sum of separable states or product states. So each of these is of this form. It's alpha I, beta I, alpha I, beta I, right? Which is simply the density matrix corresponding to a pure product state in this case, which is alpha I tensor beta I. And if I'm able to realize this bipartite density operator as a convex sum of such product states, pure product states, then I say that such a state is separable. An equivalent notion, without resorting to pure states and such, would be to say that I can realize this as a convex sum, of this kind of separable states. Okay? These are equivalent notions. All you need to do is realize that each of these, so here it's now a convex sum of product density matrices. I'm just saying that if you think this notion is too restricted, you can extend it to talk about product density matrices or separable density matrices and say that if my bipartite state can be realized as a convex sum of entirely separable states, then this state is also separable. Intuitively, this makes sense, right? Why is this a good way to think about separable density matrices? Remember, a density operator is always to be thought of as in the ensemble sense. It represents some set of pure states, which are picked according to some probability distribution, right? So it makes sense to say that if my density operator can be realized entirely from an ensemble of product states, then my density operator is also unentangled or separable. Now, of course, you can ask, but there are many ways to realize the same density matrix, and this is something I told you 2 days ago. So then how do we resolve this definition? Then the way you make this definition is to say, if there exists even one such decomposition of the density matrix in terms of product states, then the bipartite state is separable. There was a question? Yeah. Yes, yes, yes. So you can go back and forth between this by simply expanding out these density matrices again in terms of pure states, and you can redefine some sums and you can get back to the single index. So this index does not matter so much, and I'll tell you why. The operational sense in which this is separable or unentangled is the following. What does it mean to say that I can realize this density matrix as an ensemble of product states? It means that I have these two, my two favorite people A and B again. They're sitting in separate labs, space-like separated. Now, there are a bunch of pure states in A, let's say, some set of pure states in B, right? Now, what they are sharing is this probability distribution, which I will call classical randomness. So there is some shared classical randomness, but it's classical. So now A maybe does an experiment using which you can sample this kind of a probability distribution. You sample over this distribution. So if every time outcome I is realized, A tells B that outcome I is realized. So I'm going to pick at alpha I, you pick at beta I, right? So the entire state preparation of this kind of a state can happen in a way that does not involve any quantum correlations, right? It involves a shared classical random variable, according to which they are both going to pick states, and that's how they're going to construct this ensemble. So this idea that you are able to prepare this state entirely using, again, this word which I spoke about in the morning, local operations and classical communication. Yeah? Yeah, I should not have.
Anything we lost if I just say PI
No, no. Maybe to say that yeah, I could redefine things and I don't need to say this, but maybe to kind of say that I could have something which has two indices, but which need not necessarily be of the product form. That Pij need not necessarily factor into Pi times Pj.
I don't insist that the Pij
Yeah.
should be written as Pi to
Yeah.
Pi.
Yeah, one could do that.
Sigma I.
Yeah, sure, one could do that. Yeah. So, yeah, I use the two indices to kind of convey that this in itself need not be of factorizable, and you would still have a separable state. Okay. They are mixed states. Yeah, they are mixed states. Yeah, the point of writing this in the first place was to say that you don't need to restrict your definition to realizing product states on each end. A and B could have at their disposal some collection of density matrices. They sample this according to some joint probability distribution, and then they realize this ensemble. Is the idea clear? They each have some set of density matrices at their disposal. They have some joint probability distribution using which they're going to sample these density matrices and construct the state, right? So any state that can be constructed in this fashion will be a separable state, okay? And of course, like I said, there are multiple decompositions possible. So if there exists even a single decomposition of this form in terms of product states, either pure or mixed, then we say that that state is separable. So here's again an example of that. So think of, again in the 2-qubit setting, think of identity on A, tensor identity on B by 4. There are two ways that you can decompose. So this is a density matrix of 2 qubits, right? There are two ways in which you can decompose this as a set of, in terms of a set of pure states. One would be to say that I have this set of product states I could also realize the same like this, where now these are my entangled states. These are the Bell states. Because remember, the Bell states form an orthonormal basis. So when I take the projectors onto the Bell states and sum them up, I get a decomposition of identity for the 2-qubit space. So the same density matrix I can decompose in terms of a set of pure product states and also in terms of a set of pure entangled states. And this is what makes the question of separability of mixed states much more tricky to handle than the question of separability of pure states. Because here I have these extreme cases, right? If I only was aware of this description, I might have declared this to be an entangled state, to be a non-separable state, which it is not. Because I can realize the same density matrix just by each of them picking zeros and ones with equal probability and constructing the state, right? So one has to be very careful in declaring when a mixed state is separable or not. And one way to take care of this issue is when I think of a measure of entanglement, and remember we thought of at least one, which is the subsystem von Neumann entropy, right? I take a bipartite pure state, I take the reduced density matrix and I find its entropy and I say that that's a measure of how entangled the state is. So now, if I want to think about how do I quantify the entanglement in a mixed state, I can go back to pure states because I'm a bit more secure there. My measure is faithful. It vanishes if and only if the state is product. It has a maximum. It monotonically increases, etc. It is invariant under local operations, all of that. I take a nice measure on pure states, and then I minimize. For the mixed state, I minimize over all possible decompositions of the mixed state in terms of pure states. So let me write this out formally. So because it's possible to decompose the same state in many, many ways, so think of an entanglement measure. For example, the subsystem entropy. Now, I have this pure state. So let me say that this entanglement measure I call as E of psi AB for any pure bipartite state. This is nothing but the entropy of rho A, which is the same as entropy of rho B, which are the reduced density matrices, right? We saw this. So I take this measure, and then I say, how do I now talk about the entanglement content of this mixed state? I say that this is a min over all possible sets pi psi I, right? Should write this carefully. Let me just, over all possible decompositions pi, let me say phi I, such that sum over I pi phi I is equal to rho. Yeah, sorry, I'm writing this small, but I'm saying it in words so you know what that is. I'm basically saying decompose over all such pure state decompositions the average of this measure over that decomposition. Okay? So I'm saying you have multiple decompositions of rho AB in terms of some set of states phi I, okay? For every such decomposition, I can find an average entanglement for the state in terms of the pure state entanglement weighted by the corresponding probabilities. Yes? And then I minimize over all such decompositions to actually get the entanglement content of the state. Why minimize? Because that tells me really, first of all, whether I need any entanglement to prepare this bipartite state. And so if it's non-zero, the minimum could be zero, in which case means you're in something like that. Where here, for example, when you minimize, you realize that this is the ensemble which is going to attain that minimum, right? So that then tells you that this is an unentangled state actually. And it tells you the smallest amount of entanglement, or the exact, in some sense, amount of entanglement that you need to prepare the state, right? So you minimize over all possible pure state decompositions of this. And this will be a recurring theme, that we have measures for pure states, which we then do this optimization over this convex set to get a measure for the mixed state. Okay. If you simply did, so the point was that if you looked at this and you did what I just said, which is you take the entanglement of each of these, right? Each of these states is maximally entangled, right? So the average will actually just give me log 2, which is 1, which will tell me that this density matrix is maximally entangled, okay? Which it is not. So you have to allow for the fact that there are multiple decompositions possible, okay? And then use a measure for pure states, but minimize it over all possible decompositions. there's no problem with this. You just have to be aware that there are many ways of decomposing the same density matrix, and what you think of as a mixture of entangled states could jolly well be realized as a mixture of product states. And so such a mixture is actually separable and not entangled.
But how do you decide that how many basis states you're going to expand this in? I mean, there might be many basis states, right?
I did not say that this was a very tractable problem, but I said that this is how you should do it, right? So, yeah, so then, are there other ways of thinking about mixed state entanglement, right? Rather than doing this, which may not be computationally very easy task. So, yeah, this in itself is not, anyway, but yeah.
Can you answer this question? Suppose let's say this, let's say, I don't know whether it's maximally or not, but let's say it is entangled.
Mhm.
A, B. When I change the basis, they should still look entangled, right? I mean, doesn't matter what the basis.
So what do you mean by look entangled? I don't know what you mean by saying that a state looks entangled. See, I've told you that you have to be careful with basis changes. Local basis changes do not affect the entanglement content, okay? But they may not be the basis in which you can witness the entanglement, right? This is what we saw with the Schmidt form. The same state, I could rotate to a form where the entanglement is not apparent. And once I get it to the Schmidt form, then I know that this is the basis in which the correlations are manifest. So you need to go to the right basis to see entanglement, but local basis changes are not going to change the entanglement content of a state. Okay? This is not a basis change. Oh, so, okay, so this, okay, although both of these are orthonormal bases for C2 cross C2, I was not talking about basis changes necessarily here. I was just talking about the fact that the same density matrix has multiple pure state decompositions, which is something I mentioned in the first lecture. So when I write it down like this, all of these need not even be mutually orthogonal. So it's harder than even just searching over bases. One is not just decomposing in multiple bases. One is saying any pure state decomposition, where these all could be overlapping states. So it's not really a tractable optimization problem in that sense. Yeah.
So when you spoke of Schmidt decomposition, what's the problem with using the same basis here? I mean, you will also know
how do you do that for a mixed state is the question. The Schmidt decomposition you can do for a bipartite pure state, as we saw the other day, using an SVD, or you write down. See, when I have a bipartite pure state, that is when I know that the reduced density matrices are exactly equal, have exactly the same entropy content, right? And so that forms a measure, right? But the same is not true for mixed states. So actually let's write down maybe some entropic stuff for mixed states, and maybe the contrast becomes a little bit more clear, okay? So let me erase this. Yes. Yeah. This one? Yeah. Yeah. We'll just see. Okay. I'm just going to write down this for a general state. So, okay. So let's consider a few cases. So you're asking about now the joint entropy of AB, right? You're asking about, in some sense, how do I talk about the entropy, the entanglement of a mixed bipartite state? Can I purely talk about it in terms of the subsystem entropies, right? Okay, so let's look at some examples. So let me first consider the case where rho AB is simply rho A tensor rho B. Okay, this is one extreme case, right? It's a product of two density matrices. Now, what is the joint entropy versus the individual entropies? How does this relate? How are these three quantities related? What do we expect? So you think that this is going to be, what is more than the joint? Sorry. No, this is the simplest case. Okay, one way to answer this question is when you think of density matrices, think about probability distributions. What is one saying? I have a joint, think of a joint probability distribution over two classical random variables such that every one of those probabilities is a product of probability over each random variable. Why? So, okay, so if I have this situation and I'm asking you how is the entropy of this related to, okay, maybe I use different, so I say some pi times qj, or no, let me say, yeah, qai times qbj, maybe. How is the entropy of this related to the entropies of these two individual distributions? Entropy is a log. Just write down the entropy here. It's a log function. So, additive. No, basically this means that these are independent random variables, and so the entropies must just add up. The uncertainty in this is simply the sum of the uncertainties of these two. So that intuition must carry over here, and we should be able to see that S of rho AB is simply S of rho A plus S of rho B, because these are independent. Now, there is no correlation between these two systems. And one can show this with a few steps of algebra if you wish. So, but again, it goes back to just the log function factorizing for probabilities, right? I mean, becoming additive for probabilities, right? So, maybe just a few steps, since people don't seem to be very familiar with this. So, I'm going to now write each of them in their spectral form, okay? So let me say that this has some set of eigenvalues which I call Pi, this has some set of eigenvalues Qj, and then this is II. Yes? Is that okay? This is my joint state now. So, how do I calculate this entropy? It is simply, remember we said that once I do the spectral decomposition, the von Neumann entropy is just the Shannon entropy of this classical distribution, of this probability distribution. So this is simply the Shannon entropy of this distribution, which is minus sum over ij pi qj log pi qj. And then you can work this out and show that this is going to be minus sum over I pi log pi minus sum over j qj log qj. And so this is, now this is nothing but each of them, right? So this is S of rho A plus S of rho B. Now, more generally, how are these related, right? And that's where you were trying to answer, saying that something is greater and something is smaller. So that brings us to this property called the subadditivity of entropy. Okay? Which says, I think this is what someone was trying to say, that S rho AB is generally less than or equal to S rho A plus S rho B for arbitrary states which are not of this form. This inequality is saturated in the case that the bipartite state is a product state. And to see this, we again invoke this positivity of relative entropy. So I thought I should mention this because in the morning this was discussed in the classical context, right? So if I now group terms, you will see that one of the quantities that was mentioned in the morning actually shows up. So let me now write this as S of rho A plus S of rho B minus S of rho AB. This is positive. So if you recall the discussion from the morning, and if I just think of all of these as the regular Shannon entropy. Do you recognize this quantity? I don't know. Exactly. So this is the quantum mutual information between A and B in the state row. Okay? So the point I'm trying to make is when I have an arbitrary density matrix, your question was, can I not use the subsystem von Neumann entropy to talk about the entanglement? Well, which subsystem are you going to talk about? It's only for a pure bipartite state that S of rho A is equal to S of rho B because, again, Schmidt decomposition. But when I have a mixed state, I don't have this. The best way that I can do this, or the formal way that I can do this, is to go back here, do the Schmidt decomposition for all possible pure states, etc. But now we have a different tool here, right? So I could go over the proof of this, but maybe, depending. If in the end I have time, maybe we can prove this. Like I said, it boils down to proving a certain relative entropy is positive, right? And I can write that down. But now you see I have a new quantity, which is the quantum mutual information associated with, and I can write this down for any bipartite density matrix. And this quantity is always positive, is 0, so this is zero if and only if rho AB is of this form. So it vanishes for product states, is positive non-zero for any other state, namely any entangled state, and one can even associate a maximum with it. If you think back to what we did with Bell states. For Bell states, what is the mutual information? So even before going there, maybe this itself tells us that maybe this can be used as an entanglement measure. Because this is something that vanishes for product states, is strictly non-zero for anything else, right? And it will have some nice convexity properties. It's a form of, it's an entropy after all, in some sense. So this indeed is one way to quantify entanglement for arbitrary mixed states, where you don't want to go through this complicated optimization over all possible pure state decomposition. So in the quantum information literature, you will find different names given to this. So this is the quantum mutual information. This quantity, which you get by doing this, which is optimizing over all pure state decompositions, is something called the entanglement of formation. And unfortunately, these measures all don't coincide all the time. So this is an entanglement of formation because it literally tells you that. It tells you what is the smallest, or what is the amount of entanglement that I need if I want to realize this particular mixed state. This is telling you something else. This is actually telling you what is the relative entropy between your bipartite density matrix and the product of its marginals. So maybe I will write this out here. I can erase this, I guess. So this quantity here, like I said, is actually a relative entropy. And what relative entropy is it? It is the relative entropy between the bipartite density matrix and the product of its marginals. So this indeed is your mutual information, and the positivity of the mutual information simply follows from the positivity of this. And we already saw that this quantity is this positivity of relative entropy again saturates if and only if the two density matrices in here are equal. So just to avoid confusion, what I'm writing here is this state is not a product state, right? But I can define the marginals by doing the partial trace. Yeah, it's a little bit of abuse of notation, but hopefully you understand. So I'm getting the marginals by tracing out, and then I'm making a product state of these marginals. And in a sense, I'm asking how different is this joint state compared to just the product of the marginals. So it's a different way of thinking about entanglement than the entanglement of formation. I'm just trying to say that operationally, these are different. They coincide very nicely for, again, C2 tensor C2, the case of 2 qubits. The case of 2 qubits, almost all entanglement measures coincide very nicely. But beyond that, they don't. Okay? Fine. So, yeah, so I wanted to talk about the mutual information and, okay, so this is another way of thinking about mixed state entanglement. I'm not going to prove any of this, so this is all in some sense homework, I guess, or you can look up some of these references that I told you. I'll also try to share some notes where I have some of these things worked out, okay? Right, so the next thing I want to talk about is now a third way of looking at mixed state entanglement, okay? All right, any questions on this part? All right.
Saying that these two different definitions are not always consistent with one another.
Yeah.
So how do you decide like which one to follow?
So the way that people think about is, well, one is, okay, which is easier for you to compute? And obviously the answer is, for example, in a many-body scenario, this mutual information may be something that's easier for me to compute, right? Whereas if I'm in a situation where somehow I restrict my set of ensembles over which I am preparing these density matrices, or one place where the entanglement of formation really matters is if I'm thinking about doing some kind of protocol which involves sharing entangled pairs, okay? And in that scenario, what may happen is I may not be able to exactly share the ideal states that I want, but I have some noisy version of that. Then I want to ask, how much entanglement is there actually in this noisy Bell state rather than, so in those scenarios, the entanglement of formation may be something easier to compute, right? So it depends on the context. Sorry, one other thing I wanted to mention here is, okay, is there a sort of maximum value for this quantum mutual information? And at least in the case of bipartite states, bipartite qubit states, you can think about, for example, what is the mutual information? So maybe I leave this to you to compute. What is the mutual information for this state? Okay, because we think of this as a maximally entangled state. So what is the mutual information for this state? Can you answer this right away maybe, or?
It's twice.
1, 2, 3. 2, yeah. So this is actually 2 because, yeah, you have, both of these are 1 for this case, this is 0. So technically, the measure that people define often is not just I, but half of this, if you want to normalize it to make this 1. Okay, so this is one entanglement measure that people look at. Okay, so another way of thinking about mixed state entanglement, or about sort of detecting entanglement or identifying whether a state is entangled or not, is to think in terms of witnesses. So let's say I'm not necessarily interested in quantifying entanglement, but I just want to witness entanglement. I want to certify whether a given state is entangled or not, right? And this idea is called an entanglement witness. So I'm just throwing some terms here. You can use Google Scholar and find many articles on this subject. But I want to talk about one nice formulation of an entanglement witness, and this also has very nice mathematical structure. So this is the so-called Perez-Horoditsky criterion, or the positive partial transpose criterion.
Barely visible. The letters are so small.
Ah, I'm sorry. Yeah.
Formulas little bit work.
Yeah. Sorry. Okay. These are proper nouns, so it's okay. But this is positive partial transpose. Okay. So what is the transpose of a matrix? We all know that, right? Now, obviously I'm talking about partial transpose. So let's first just look at the transpose of a density matrix. So I have, just think of a single qubit density matrix. Let's say that this has some decomposition like this. Maybe not necessarily diagonalized, okay? So it is generally of this form, some Cij, Ij, right? This is how I would expand this. What is the transpose of this? So I'm just going to think of transposition as interchanging these indices here, right? So this is Ji, okay? Now think of this transpose as a map on the set of operators, right? This is a matrix already, yes, but now I'm asking you to think about a map on this space of operators or space of matrices, okay? And this map just does this transpose. Now this is a map. Now this state that I get, or this operator that I get after doing the transpose, you realize has the same trace as this. If this is positive, then so is this, okay? So I'm not proving all these statements. I hope you can, I hope you see that. So the point is, if this is a density operator, which means it's trace 1 positive semi-definite, then so is this. So then rho transpose is also positive semi-definite. Rho transpose also has trace 1. So this is also a valid density operator. So the transpose map is something that preserves trace and preserves positivity. Okay, so this is something that we will call a positivity preserving map. Nice. Now, why partial transpose? So now, if I think of a bipartite density operator, so think of a bipartite density operator where I don't do anything on one subsystem and I apply this transpose map only on the second subsystem. It may not be first or second, I'm just writing it for an example's sake. So it's identity on the first and this transpose map on the second. I'm putting hats to say that these are maps on operators, okay? The question is this state, or is this matrix that I get out of this? So sometimes people write this with a little t sub b on top to indicate that you have done the transpose operation on the second subsystem. Question is this always positive? Okay? And I wouldn't be asking this if the answer was yes, because there's nothing more interesting to say then. The point is that this partial transpose is not a positivity preserving map. So think of the transpose map alone. What one is saying is if you extend it beyond a single system, then the map is no longer positivity preserving. Now, if there was a map which preserved positivity across any extension, such maps are called completely positive maps. They also play a very special role in the context of quantum information, but that's a separate lecture altogether. But just noting that this kind of a map is something that preserves positivity on a single system, but once you extend it, that property is gone. And I'm going to show you this just by example. So let's work this out for our favorite Bell state. So think of this density matrix. And we already wrote this down yesterday for one of maybe the tutorial, I'm not sure. Oops. So this is now my bipartite density operator, okay? What do I get when I do a transposition on subsystem B? Nothing happens in the first term. The second term, only these two have to swap, right? So I have 0, 1, 1, 0, okay? In the third term, again, they swap. So I get 1, 0, 0, 1, and then 1, 1, 1, 1. Overall half. So maybe let's write this out as a matrix. And how quick are you in diagonalizing 4 cross 4 matrices? So the original matrix we started with looks like this, right? It's half, 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 with zeros everywhere else, etc., right? It's 4 cross 4, of course. But now you look at this transposed matrix, then, so, okay, maybe it's useful to write this out properly and show how the transposition, yeah, sorry. You're doing the partial transpose on the second subsystem. So the reason I split this matrix out like this is because you realize, with a little bit of thinking and working out, that if you do the transpose on the second subsystem, then this is essentially the swap that happens. So now the matrix I get is this. And now the question is, what are the eigenvalues of this matrix? So, I mean, the question is it positive, right? That's the question we were trying to answer. This is a density matrix, it's just coming out of this, so this is positive. To check if this is positive, I need to write down its eigenvalues, right? Yes? Anybody already solved that? No? Yeah. Uh-huh.
The middle two cost of the 4 entries,
Yeah.
you just take the sub-matrix induced by the second row, second and third rows and second and third columns. In the bottom matrix.
Mm-hmm.
Just put a little box around the 4 entries.
Oh, here. Okay.
There is a principal matrix which is not positive.
Yeah, okay. Yeah. Sure. Yeah. So you can just look at this actually, and you know that, yeah, there is a principal matrix here which is not positive definite, and so you know that this matrix therefore is not positive semi-definite. But I'm not sure if everyone is familiar with that concept here. No, okay. In which case you do it the good old way, which is you diagonalize this and you get the. So you will see that you get one negative eigenvalue here. Okay? So this matrix is not positive. So So by doing a partial transpose on one subsystem, you have moved from a density matrix to something which is not a positive matrix. So this is not a valid density matrix anymore. In fact, these kind of maps are what you think of as unphysical maps, because these are not things which you should be able to realize in a lab, right? This is not a valid quantum transformation. Quantum transformation has to take positive matrices to positive matrices, density operators to density operators. But this partial transpose is actually an unphysical map. But it is a map that witnesses entanglement for you. Because now I'm going to go back and say, okay, I did this for an entangled state. But suppose I had done this for a product state. Suppose I had done this partial transpose for something which was of this form, rho A tensor rho B. I'm doing nothing to the first system. I'm doing the transpose on the second system. So rho A remains as such. Rho B becomes rho B transpose. And as we said, if you just do transpose on one system, it continues to remain a density matrix. So the point is, when I do this partial transposition on a product state, I retain positivity. Okay? And you can extend this now to separable states, because I can now put a sum over IPI and put different density matrices here, and it continues to remain positive.
So when we do partial trace, then physically it means that we are
Partial trace is different from partial transpose.
Yeah,
Huh.
so
Okay.
we mean that we are just neglecting the degrees of freedom of second subsystem.
Yeah.
So physically, what does this partial transpose mean? That what are we doing with the degrees of freedom of?
The transpose, in doing the transpose, you are basically just doing a change of the indexing of the basis, right? That's pretty much all that you're doing. So I don't know how to give a more physical explanation for that. But like I said, the partial transpose is actually not even a physical operation. It's here it gives you a nice theoretical tool to witness entanglement, right? Yeah.
Just asking, so this tool was just found by intuition.
Okay. So let me complete the discussion and then say how, or is it just how did one arrive at this? Is your question, right? So, okay. So let me, yeah.
Converse is also true. If you show that the partial choice is negative, then it's non-separable.
Yeah, so one way is true. So the question is it both necessary and sufficient? Okay. So having a positive partial transpose is necessary for your state being separable, right? But having, if your partially transposed state has a positive, is fully positive, it does not necessarily mean that your state is separable. So you could have entangled states with positive partial transpose. However, in the case of two qubits, in certain dimensions, this becomes a necessary and sufficient condition. So I'll just write this out. Yeah. So what does this summarize? So I hope everyone sees that if I have a separable state, then the partial transpose is always going to be positive. Okay? So let me state it like this. So if rho AB is separable, then rho AB, I'm just going to write transpose B, doesn't matter where you do the transpose, is always, let me say, non-negative. Okay? So this is a necessary condition for separability. But is it also sufficient? It is sufficient. It was shown. So this is the famous paper, this Perez-Horoditsky paper, shown that it was sufficient only in certain dimensions, namely C2 tensor C2 and C2 tensor C3. In other dimensions, you could have entangled states which also have a positive partial transpose. So just having a positive partial transpose in that sense is not sufficient to declare that your state is separable, except if you are again in the 2-qubit scenario or in a qubit, and this is what we call a qubit. So in a qubit scenario.
You mean some positive partial transpose, not all partial transpose positive.
In other dimensions.
In higher dimensions.
In higher dimensions, if you have a negative eigenvalue, it's clearly entangled, right? That is fine. But if you have a positive operator at the end of doing the partial transpose, you can't declare your state to be separable. So there are what are called PPT entangled states. So there are states which are called PPT entangled. Which means you know them to be entangled in other sense, okay? But when you do the partial transpose test, you actually end up with a positive matrix.
When you do partial transpose test, you do partial transpose in all subspaces possible or only in some of them?
Oh, this is still only for bipartite systems, right? It's still only for bipartite systems. So I can do the partial transpose on either of the subsystem. It wouldn't matter. Right. So this, in some sense, addressed this question of being able to witness entanglement. So now the question is, why partial transpose? So the reason that this partial transpose works is because it's an example, like I said, of a map which is physical as far as a single subsystem is concerned. See, what is one trying to do? One is trying to somehow detect correlations across a pair of subsystems. And an ideal candidate seems to be a map or a transformation which is physical at the single subsystem level, but does not extend that physicality to multiple subsystems. And a map which is positive but not completely positive is an ideal candidate for that. So there's a lot of people who investigate other such maps, which are somewhat artificially constructed though, nothing so neat as the transpose. So there are a few other maps. So maybe I'll direct you to some. So there is something called a realignment map. Okay. This is in fact a different way of doing. So like I said, the partial transpose is just a relabeling of basis indices. Why only transpose, right? One can think of relabeling these indices in other ways. So there is something called a realignment map, which again has this property that for a given system density matrix, it preserves positivity, but when you extend it, it does not preserve positivity, right? Then you can even think of something like just complex conjugation. Now, complex conjugation by itself is not a physical map, right? But it turns out, so this is somewhat different category from PPT and realignment, but this in fact gives rise to a measure called concurrence. I'm unfortunately not going to have time to talk about that, but just want to say that these transformations which we think of as unphysical normally, so the combination of complex conjugation and transpose is fine. That's your Hermitian conjugate, right? But
Time reversal.
exactly. Well, so yeah, so you think of this time reversal map, right? And that can be used to construct a measure called concurrence, okay? Which I'm probably not going to talk about because it's just going to get too much in one lecture. But I hope that gives you some, I think someone asked me, how did they come up with this map? So this is the thought process, that you have a map which is physical or positivity preserving, and then now once you extend it beyond that breaks down. So there is, in a sense, a deeper intuition for this. There is a sort of isomorphism between states and operators. There's an isomorphism where you can associate with, so you can associate a state in a larger Hilbert space with an operator in a smaller Hilbert space, right? And through this association, you will realize that there are maps of this kind which, when acting on entangled states in the larger Hilbert space, will give you something unphysical. So this probably was how Horodetzky and Perez came up with this idea, and it very neatly works in the case of 2 qubits, but unfortunately it does not extend much beyond that. If you are into things like functional analysis and so on, this is related to a very nice geometric idea called the Hahn-Banach theorem. Anybody familiar with these names? Okay, then let's not do that. Yeah. Okay. All right. So I have half an hour more. Okay. Questions on this PPT criterion? Yeah.
So, is it true that separable states, for separable states, you never violate Bell's inequality?
Yeah. For a separable state, you will never violate Bell's inequality is correct. Yeah. Yes, yes, yes. Again, however, the converse may not be true. I will give you an example of an entangled state, a non-separable density matrix, which does not violate any Bell's inequality. So there are examples of that kind. Okay, and this is what I was, somebody asked me this question the other day also. So, okay, so maybe I can move on to discussing some of these other things. So this PPT criterion also gives us maybe a measure of entanglement in a different sense now, and this measure is basically related to how negative is this partially transposed matrix. Remember, in the case of this maximally entangled state, we saw that you get one negative eigenvalue, right? Now you can ask, suppose I look at, in a general setting, I look at this partially transposed matrix and I look at the modulus of its negative eigenvalues. I can use that as a measure of entanglement, and that measure is called negativity. So let me just write this down here. So there is an entanglement measure called negativity, which is basically sum of the negative eigenvalues of this partially transposed matrix. Of course, you have to do modulus. Yeah. So it's simply the sum of the negative eigenvalues. You can think of this as a measure with appropriate normalization and all that. In the 2-qubit case, this measure, the concurrence measure, the subsystem von Neumann entropy, the mutual information, they all match. Okay? So they all sort of converge to the same thing in the case of a 2-qubit system. But beyond that, they each seem to capture different facets of entanglement. Yeah. So that's, yeah. So in a sense, this is saying how negative is your, so you can think of this as, so this matrix is in some sense less than or equal to 0, and then you're asking how much smaller is it to 0. So you can, so normally you know that the trace is supposed to be 1, right? So you're deviating from 1 by this extent. So that's the sort of idea. Yeah.
All these measures of entanglement, right, if we extend it to a pure state, do they all agree?
Yes, yes. For pure bipartite states, see, the negativity is a proper witness of entanglement only for 2-qubit states, even in the pure state case, right, or qubit qubit case. So even there I have to add the caveat that yes, for 2 qubits it agrees. But
you transpose to deviate from 1? I mean,
sorry?
how you transpose to deviate trace from 1? In this example, it was 1/2 plus 1/2 minus 1/2. The trace was still 1.
Yeah, yeah. The partial transpose, you mean?
Yeah, partial transpose.
Yeah.
So how it could change trace?
So I'm not saying that it's changing the trace. I said that it basically captures, so one, so let me write this out exactly what I have here. It should maybe say, yeah. So I'm saying, if I were to look at the trace norm, okay, how much does that deviate from 1? And say half of that. So that's what this will boil down to. Okay? The trace norm will no longer be 1. Okay. Yeah, so maybe the last 20 minutes, I will talk a little bit about multi-party entanglement, right? So many people asked me about this, so I want to at least talk about the GHZ and the W state. So basically, this is an invitation to quantum entanglement, right? Because there are many, many unanswered, unaddressed questions here, which are very interesting mathematically as well as from a physical point of view. So I'm just trying to point out a few interesting questions that you can ask here. Okay, so multipartite entanglement. So let's go beyond the 2 system case and let's talk about 3 qubits, right? And I can think of writing something exactly like a Bell state for 3 qubits. So I'm going to write one such state, and I'm going to give it a somewhat complicated name based on this is basically the initials of the people who identified some nice properties of this state. So this is what it looks like. So it looks like a Bell state. It looks like you have extended the idea of a Bell state to 3 qubits. You again see, so again, let's say this is written in the sigma z basis. So you again see some correlation in the sigma z basis. If you measure, you know that you're going to get. So this state has many interesting properties. The GHZ stands for Greenberger, Horn, and Zeilinger. Zeilinger being again one of the people who won the Nobel Prize in 22. I would point you to chapter 4 of Preskill Notes for a very interesting discussion on how you can sort of talk about this Bell non-locality type issue using this state. So if you distribute the state among 3 parties, and let's say they try to measure complementary observables on the state like sigma x, sigma y, sigma z, they can, by trial and error, come to a wrong conclusion about the set of outcomes that they can assign if they go purely by classical intuition. Okay? So it's an interesting state where you don't even maybe need a Bell inequality to show a violation, just by argument, which I again am not going to be able to go into now, by trying to assign values to some combination of sigma x, y, and z, you will arrive at certain inconsistencies in this state. Okay? And you can show that not all possible value assignments are allowed because of this certain non-locality in the state. But that's not what I want to talk about. I want to talk about, okay, so now there are 3 parties and they seem to be entangled. But can I reduce it now to a bipartite setting? Can I ask how entangled is A with B, B with C, and C with A in this state? How would I do that? I do a partial trace and I get a reduced density matrix. So this is a state of A, B, C. Let's say I trace out C. And I get row AB. Can you tell me what state this is? the mechanics of partial trace is the same. I write down all possible terms, but then there are some terms which will go away. So I hope you see that what you get is this. Now this is a mixed bipartite density matrix. Go back to the beginning of this lecture where we defined when a mixed state is separable and non-separable. And then think about, is this a separable density matrix or not?
Shouldn't be, because your trace out should be a mixed state.
It's mixed, but is it entangled or separable? Between A and B. This is separable because I can write this like this. Yeah, product over AB, another product state over AB, and an equal mixture of that. So here is a tripartite state which appears to be very highly entangled. I won't use the word maximally entangled because I haven't told you what that means in this context, which appears to be highly entangled. But when I trace out one out of the three subsystems, I land up in a separable state. And by symmetry, I hope you will see that this is true also for rho BC, rho CA, and rho AB. They are all separable states. So this is a state where the entanglement truly resides only in the tripartite setting, and any bipartition that you do of the system breaks all entanglement, and you're left with purely separable states.
So this rho A is separable, it means that we can write in the form of psi psi.
Not for mixed states, no? For mixed states, you may not be able, you're not going to be able to write. That's only for pure states. For mixed states, you should be able to realize it as a sum of such product states, which is what you see here. So this is one example to show you that multi-party entanglement is more complicated. It is not, so you can have states like this. So again, I guess I should point out that there is a connection to something called Borromean rings. So people like to give a sort of pictorial representation of the GHZ state using something called the Borromean rings, which is basically a set of 3 rings which you may have played with or seen at some point, where if you remove one of them, the other 2 come separate. Okay? You have a set of 3 rings which are entangled together, which are joined together, but if you pull out one of them, then 2 of them come out separately. So there are also Borromean triangles and so on, and one finds this kind of a symbol in many ancient monuments, including in a temple not far away from where I live in Madras. Okay? All right, but this is not the end of the story for multi-party entanglement, right? So there are also other states where you do have both tripartite entanglement and bipartite entanglement. So I want to give you another such example. So this is a state which I simply call a W state, which has this form. Okay? And now once again you can do the same. This is a joint state of these 3 systems. You see there is some sort of permutation symmetry in the state. Okay? It's using these 3-bit strings where I'm just permuting them, right? Now when I do this reduced density matrix here, maybe I call it something else. So maybe I don't need to write out the whole thing, etc. But okay, maybe it's useful to just see this for you to see what one means, So let me again write this in the same basis, just to contrast with the GHZ. Okay? There's no 1, 1 in this case, right? These are the 3 states. I write down the ket and the bra. I do the partial trace. I end up with a mixture like this. Okay? Now, is this a mixture of separable states or not? So, look at these 2 terms. And these are exactly like those middle terms even in the case of the partial transpose in some sense, the other example that we did. So what are these terms like? These are of the form 0, 1, tensor 1, 0. This, neither of which is a valid state in each subsystem. Okay? This is not a state. This is not a state. This is unlike 0, 0, 1, 1, which is what we had in that case, which are simply density matrices corresponding to the 0 state and the 1 state. These are not positive operators, right? So here in this mixture, I have terms which are not actually of this kind, that you can write it as a state in subsystem A, tensor a state in subsystem B. Do you see that? So this is different from the GHZ case, and so now this is one way of seeing it. You can go ahead and do the PPT test here. So you can do a partial transpose of this, and in fact you will find that it has negative eigenvalues. So if you do the partial transpose, you will end up with, you will see that this is not positive, okay, which kind of conclusively tells you that this density matrix is not separable. Okay, so you already see it from here that at least in this expansion you're not able to see this as simply a sum of tensor product of states in each subsystem. But if you do the partial transpose test, that kind of conclusively will tell you, and maybe I leave that as homework for you, it conclusively tells you that this is non-separable. So here's an example, and similarly you can do the other 2 reduced density matrices, and you will find that they are also not separable. So this is a state which has some entanglement in the tripartite sense as well, but also in the bipartite sense. So there is both tripartite entanglement and entanglement across every bipartite cut of this tripartite state. So the GHZ and the W state are considered to represent 2 classes of entanglement as far as tripartite systems are concerned. That you could have maximal or very high tripartite entanglement with 0 bipartite entanglement. Or you could have these kind of states where you have both tripartite entanglement and entanglement across every cut. Okay. Now, then people go ahead and define measures called genuine multi-party entanglement. So you take some measure of entanglement for the multi-party state and then remove from that all possible bipartition, the entanglements of all possible bipartitions, to quantify how much genuine multi-party entanglement there is, and so on, right? But in the last 10 minutes maybe, I want to tell you one nice use. I should at least tell you a little bit about what I do, which is quantum error correction. So, yes, both of these can be generalized to the n-partite setting. Okay, so you're saying that if I, okay. So the way one would ask that question is to say, if I have an n-partite state, is there some k such that when I make that k partition, the states become separable? So indeed, people ask such questions. In fact, people ask the opposite question. They say that if for every k up to n by 2, I always have some entanglement, then such states are called absolutely maximally entangled states. And people have some constructions of these kind of states and so on, and they have some nice applications. But yes, you can study this, and there's some characterization of this known, right? Like I said, the opposite is known, that you have very highly entangled states, where for every k up to n by 2, if you have an n-party state, the state continues to be entangled. And the signature of that will be that the reduced density matrix will be a maximally mixed state for that cut, right?
Is it possible that, like in this case, if rho A is separable, then rho BC and rho CA is also separable? Can it be possible that if rho AB is separable, then rho BC can be entangled?
So, yeah, I don't have a answer for that, because I don't know if that is possible. I don't know of any examples like that, and I want to say that it is not possible, but I can't think of exactly a reason why, or yeah. So, yeah, these two states are clearly symmetric. One has, that has a that is cyclic, and this is also symmetric under interchange of 0 and 1, right? Yeah, I don't know of examples where that may be possible. Okay, so one last point about these kind of multi-party entangled states. What are they useful for? So it turns out that in particular this GHZ state, I can think of these two states. Think of them as spanning a two-dimensional subspace. So what space am I in? I am in a space of 3 qubits. So I am actually in dimension 2 to the 3, which is 8. And in this 8-dimension space, I pick a pair of states, and I label this 0L, and I label this 1L. Okay? This L stands for logical for me. So I have picked a two-dimensional subspace of this 8-dimensional space, which is C2 tensor C2 tensor C2. It turns out that this subspace acts like what we call an error correcting code for a specific kind of error, which is the bit flip error. So let me back up a little bit and say, what do I mean by that? So now think of these labels here as classical indices. Think of this problem of storing or sending classical information in bits 0 and 1. And now you have, with a certain probability, your system is not stable enough, so it's going to flip the bit with a certain probability. So there's a certain probability for 0 to become 1 and 1 to become 0. Okay? So this is what we call a bit flip error. So it's often written like this. So there's a certain probability P with which the 0 can become 1 and the 1 can become 0. And then there's a certain probability 1 minus P with which nothing happens. This is an example of this communication channel, which I think was mentioned in the morning briefly. You can represent this in terms of these conditional probabilities that were written down in the morning, right? So now classically, how do we address this issue? If I know that there is a certain probability for each bit to be flipped, but I assume that I have a reasonably stable channel, so this probability is much, much smaller than 1. It's not very high, the error probability. Then the natural thing to say is you introduce some redundancy. You do some coding. You introduce some redundancy, and in the place of every 0, you send 3 zeros. In place of every 1, you send 3 ones. And this is the simplest, or maybe one of the simplest classical error correcting codes that you can think of. This will help you resolve the issue. Why 3? So that you can do some kind of majority voting at the end and say, okay, the probability of a single bit flip is P. The probability that 2 are going to be flipped in a set of 3 is smaller, it's P squared. I assume that 3 flips are never going to happen almost. So I look at every set of 3, and depending on whether I had more zeros or ones, that naturally tells me what happened, right? So that I can then detect the error and I can correct for it, okay? Which is sort of the ingredients you need to have error correction. Now come to the quantum case. The same thing can happen. I'm trying to store quantum information in a memory, or I'm trying to send, like in the morning we were talking about sending one half of an entangled pair and so on. I said ideal noiseless channel, but that's an ideality. So now assume that there's a chance that this entangled state, one half of the entangled state, is going to undergo this kind of bit flip. Can I do the same thing in the quantum case? Can I replace every 0 by 3 zeros and every 1 by 3 ones and get a quantum error correcting code? Now the issue in the quantum case is I'm not just sending zeros and ones. I'm sending alpha 0 plus beta 1. I may want to store alpha 0 plus beta 1. So now you may say, well, if you want to do that, maybe you just send 3 copies every time you want to send something. So can I do three times of this? Because I need redundancy in some form. That's sort of the idea in coding, right? I have to somehow introduce redundancy so that it protects me against noise. But can I do this? Somebody said no. Why not? Yeah, exactly. I told you in the morning that if I don't know what these are, if I don't know my alphas and betas, which I don't expect to know all the time when I'm doing a computation or in communication, then I cannot do this. I cannot clone an arbitrary quantum state. I cannot make copies. So here is where entanglement comes to the rescue, and we say, okay, instead of this, which we cannot do in the quantum case, think about doing this. This I can do, okay? Because this is basically a modified version of this GHZ state where for arbitrary alpha and beta. If alpha and beta are exactly 1 over root 2, then I get back my GHZ state. For any other value, this is still an entangled state. So this is what I mean now. So instead of sending or storing an alpha 0 plus beta 1, I instead send or store this alpha 0, 0, 0, which takes the place of a single 0, and 1, 1, 1, which takes the place of a single 1. Although it looks similar to the classical case, there's something which is fundamentally different. I have gone to an entangled state. I need this entanglement in order to make my information redundant in some way or introduce redundancy and make it resilient against noise. So how it works as a bit flip code, etc., maybe one can discuss some other time, but I just wanted to point out that these kind of multi-party entangled states are actually the necessary ingredients for constructing quantum error correcting codes. Okay, so maybe I stop here. I know this last lecture was too many things, but hopefully still take away something from it. Yeah. Questions? Yeah.
So I understand that loop learning theorem does not allow us to copy this statement, but
Yeah.
it allows us to copy, let's say, 0.
Yeah.
But here we have to do on both the things, both 0 and 1, right? So how do we do this?
How do we do this is, remember in the morning we prepared a Bell state. Yeah? So we said you have a Hadamard, you have a C naught. Now you put one more line here. You put one more C naught. Okay? That's it.
I was just wondering, like, what is more common as an error? Is it like phase decoherence or?
So I must say that I think of bit flip as not the most physical noise model in the case of quantum bits. Because typically the bit flip channel is studied as a symmetric channel, although I wrote P and, yeah, so usually what we say is that, okay, let me put it this way. The P is the probability for the 0 to go to 1 and the 1 to go to 0. But typically in my quantum case, my 0 and 1 are energies. They have some energies associated with them, right? So my 1 is typically the excited state of some system. So I would argue that there is a greater probability for my 1 to decay to 0 by spontaneous emission of a photon rather than for my 0 to get excited to 1, which is a thermal process. So these two processes are usually not symmetric in the quantum case. So the bit flip, therefore, is a slightly artificially constructed noise model. Phase decoherence, on the other hand, is much more natural, I would say, in the quantum case. Yeah. Sorry? Are there ways to do away with phase? Bit flip, which is a sigma x, it's a sigma z. So instead of 0, 1, you now work in the plus minus basis, the complementary basis. And then you have an error correcting code for phase noise. We can discuss offline. It's probably going beyond, yeah. Yeah. The Hadamard is not there. I wanted to say that, yeah. I mean, in the morning we did the Bell circuit, yeah, yeah. I wanted to say that the Hadamard is not there. The Hadamard would mean that you always have the GHZ state. Now what comes in here is some state which is already in this superposition state. Yeah, yeah, thanks. Yeah, yeah.
Ma'am, is there any measurement of extent of entanglement and qubit is
A
studied?
qubit. What do you mean by how much entanglement?
Monogamous of that entanglement. So you told that if one qubit is entangled with another, it has some extent up to which it can go. So
Yeah, yeah. I actually did not have time to talk about this concurrence idea. But okay, let's think of any entanglement measure maybe. And let me write down what I mean by monogamy. So there's some entanglement measure. So let's say it's a tripartite situation. So I have some psi ABC, okay? So here's an example of what a monogamy relation would look like. It says that the extent of entanglement that A can have with B in this tripartite sitting. Now these are all the marginals, the reduced density matrices you get by tracing out. This is the extent of entanglement that A can have with C is somehow bounded by the extent of entanglement that A can have with BC. Okay? So in particular, if one of these is already maximally entangled, then this will also be then maximally entangled. The other one has to be 0. Okay, so between ABC, if A and B are maximally entangled, then AC will have to be 0. If this is something less than maximally entangled, then there is a trade-off. This will kind of bound, this kind of provides a constraint, and then you can play around with how much entanglement can you distribute between these two. So there's a nice paper by Wouters, it's a PhysRev A sometime in the 90s, on entanglement distribution. I also wanted to point out a Reviews of Modern Physics article, but maybe I'll send these references to you over email, yeah. Which talks, so this is entanglement distribution, or more commonly known as monogamy of entanglement. So this kind of a relation constrains how much entanglement you can have, A can have vis-a-vis B and C.
Okay, I guess no other questions, so let's thank Prabha for a really fantastic set of notes.
Thank you.
Okay, so I think you have already received a mail. So today we have a banquet from 7 o'clock. So we have also arranged for a visit to the museum. So we have a museum here. So it can take about 20 people comfortably, but we'll arrange more visits. So I think the people who are living next week, they should go today. And then some of you also can join. And then I'll try to have more visits later. I think many of you probably also have gone earlier in the earlier schools. Yeah. So it's basically when you just go out of this door, it's just that end of that corridor.
On this floor?
No, on this floor. It just go straight. Just yeah.
Banquet is where
Banquet is where we have lunch and breakfast basically. So we'll start at 7, so you have about an hour for the museum.
Thank you.
Yeah, thank you. So,
You create one here?
no, my flight is later to